Okay, so very good afternoon to one and all, and I welcome you all in the next lecture of heat transfer. In the last lecture, we have discussed this particular problem on a composite wall, and I think this problem is very much important in the sense of a gate examination and the competitive examinations for mechanical engineering. Okay, take any examination, you'll find such type of problems from heat transfer subject. Okay. So, first of all, let me know whether my voice is audible to everyone and can you see my presentation?
Yes, sir.
Great, great. Thank you. So, in this problem, what we have discussed that there is one composite wall, and this composite wall having the layers of walls, or we can say that different layers, and these layers are not in a single format. Okay, some layers are perpendicular to the another layers. Okay, some layers are B and C layers are perpendicular, B and C walls are perpendicular to A and D wall. Okay, so the same format is not applicable whatever we have used in the previous examples. Okay, where in the previous example the wall layers or the walls are in the single format only. Okay, they are in a series connection. If you discuss the electrical analogy, then they are in a series connection only. But here in this particular problem, the format is somewhat changed and mixed the format is shown in figure. Okay, so how to tackle with such kind of a problem? For that purpose, you need to understand how to convert the three-dimensional figure into two-dimensional figure. Okay, so simple way, we have to consider just the thicknesses of this particular wall. And as we know that as the some walls are in a parallel and some walls are in a series, so that the area available for the heat transfer will not be a constant one. Okay, will not be a constant one. So it will be changed for each wall. Okay, so area for wall will be this one, this much. Okay, so area for B wall is up to 3 centimeter. Okay, 3 multiplied by 10 centimeter. Area for the C wall is 7 multiplied by, or we can say that the 10 multiplied by 7. Okay, 10 multiplied by 7 will be the area available for C, and for D 10 multiplied by 10. Okay, so that will be the area available for the heat transfer for each slab, and it is not the same one for each slab, and it is different for the each slab. Okay, so in that case we have to separately find out the areas. Okay, thermal conductivities. Then next thing is nothing but we have to draw the electrical analogy. Okay, electrical analogy. So in this first of all, we have drawn the 2D diagram, or one dimensional heat transfer diagram. Okay, so that provides you a clear picture about the heat transfer, and on that basis it will be easy to draw the electrical circuit diagram. Okay, so analogous electrical circuit diagram for the heat transfer. Okay, and once you will get the analogous heat transfer diagram and analogous heat transfer diagram, then it will be easy to analyze that which resistance, okay, heat transfer resistance is in a parallel and which resistance in a series. Okay, so by simple analysis we can say that the resistance B and resistance C, thermal resistance B, or the resistance of wall B and resistance of wall C are in a parallel. Okay, are in a parallel, whereas A and D, we can say that they are placed in a series. So we need to find out the equivalent thermal resistance. Okay, for the B and C. Okay, first of all we have to determine all the three resistance. Okay, so resistance is nothing but what? Resistance is equal to L divided by K multiplied by A. So suffix we need to provide according to the wall nomenclature. Okay, for A wall we have to provide the A suffix, for B wall we have to provide the B suffix, for C wall we have to provide the C suffix, and for D wall we have to provide the D suffix. Okay, but the formula is the same one, that is L divided by K multiplied by A is the formula for the thermal resistance. By considering that only, that formula only, we have finding out the resistance for the wall A, resistance for the wall B, and resistance for the wall C, and resistance for wall D. But here the problem is about the parallel resistance, okay, about the parallel resistance. So in that case we need to find out the equivalent resistance for those parallel resistance. So we know the formula that equivalent resistance 1 upon R equivalent is equal to 1 upon RA plus 1 upon RB. So equivalent resistance, for that purpose we have to use this particular formula, as we are applying such kind of a formulas in electrical circuit. Same kind of a formula we need to apply over here, and we have to find out the equivalent resistance. So RTHBC we have calculated, and further once we determine the equivalent resistance for the parallel arrangement, then just add up that all the resistance, so we will get the total resistance. Okay, so we know that heat transfer is equal to overall temperature difference divided by total thermal resistance. So just put up this particular values, dt overall temperature difference, so initial temperature minus final temperature, that is the overall temperature difference, divided by total resistance or summation of all the resistance. Okay, so we will get the heat transfer rate or heat loss or heat gain. Okay, so in this manner we have to solve such kind of a problems. Now today in this particular lecture we are trying to understand the thermal contact resistance, important terminology, and the second terminology is the overall heat transfer coefficient. Okay, thermal contact resistance and overall heat transfer coefficient, that two terminologies we are trying to understand in this particular lecture, which are related to the composite wall only. Okay, which are related to the composite wall only. Now let us consider this particular diagram. Okay, so important thing, what is the assumption in this particular diagram? So here first of all we are considered the one dimensional heat flow. Okay, so one dimensional heat flow, so the heat is flowing only in the x direction. Okay, now in this particular diagram we are considering that the contact between these two walls, okay, A and B wall, is completely firm contact. Okay, is completely firm contact. That is nothing but what, each element of wall A and each element of wall B are in a contact. Okay, are in a contact. And in a similar fashion, so each element of wall B is in each surface element of wall B. Okay, so at point 3 each surface element of wall B is in contact with each surface element of wall C at point 3. Okay, but what happened in general? Okay, what happened in general, we know that even the polished surface is having some roughness. Okay, even the polished surface is having some kind of a roughness. Roughness means what, there are some crust and troughs on that particular surface. Okay, so that this crust and troughs will form some voids in when they contact with when they physically contact with the another surface. Okay, so when they physically contact with the another surface, they form some voids. Voids means what, small holes. Okay, voids means what, small holes, and the air will trapped in that particular small holes. Okay, the air will trapped in that particular small holes. So we cannot say that how much area is available for the heat transfer at this particular interference point. Okay, initially what we have considered, we have considered that the contact between adjacent layer is perfect one. Okay, the contact between adjacent layer is perfect one, and at the interference there is no fall of a temperature. Okay, at the interference there is no fall of a temperature. What it means, at the end point of A wall, what is the temperature? T2 is the temperature. That temperature will be considered as the entry temperature for the B wall. Okay, the exit temperature of A wall is considered as the entry temperature of the B wall. In a similar fashion, the exit temperature of a B wall is considered as a entry temperature for the C wall. Okay, so that by considering this only, we are solving the previous problems. Okay, now here what is considered, that the interference and there is no fall of a temperature at this particular interference. Okay, there is no fall of a temperature at this interference. This is our assumption, and the temperature is continuous, although there is discontinuity in temperature. Okay, so we are considering that whatever the exit temperature for wall A, that is the entry temperature for wall B. But in reality, it is not happening. Why it is not happening? As we have discussed that every wall or every surface, even the very polished surface is also having some kind of a roughness. Okay, some kind of a roughness. Roughness is nothing but what? It is having some crust and troughs. You check these kinds of roughness. So if you use some devices, okay, telescope, and if you check the polished surface also, then also you will get such a crust and troughs. Okay, उतार चढ़ाव आपको देखने को मिलेंगे उस surface पर. So that is nothing but what? It is that particular surface is having some roughnesses. Okay, or it is not a plain surface. Okay, it is not a plain surface. So what will happen when this particular surface is in contact with the another surface? When this surface is in contact with the another surface, so complete surface area of one wall is not in a contact with the another surface because of this particular crust and troughs. Okay, so there will be small voids present between two contact surfaces or between two walls. Okay, there are some small voids. Voids means what? छोटे छोटे होल आपण म्हणू शकतो. Small voids are present, and these voids or these gaps are filled by air. Okay, these gaps are filled by air. Okay, and this particular air will provide lot of resistance for the flow of it. Okay, this air or this particular voids will provide a lot of resistance for the flow of it, because we can say that because the area available for the heat transfer is lesser than the geometric area of that particular surface. Why it is happening? Because the area available for the heat transfer is lesser than the geometric area. Okay, is lesser than the geometric area. So that we can say that the resistance will be there at the interference point. The resistance will be there at the interference point. So interference means what? Where the two walls are connecting each other, or where the two walls are in physical contact. So that particular line or that particular point will be considered as the interference of those two walls. Okay, actually we are considering that the complete area, whatever the area is there available for the heat transfer, that particular area is completely in contact with the wall A. That is our initial assumption. But it is not happening in such a manner, that because there are some voids present, there are crust and troughs, there is some roughness, and because of that the area available for the heat transfer is lesser than the geometric area. Area available for the heat transfer is lesser than the geometric area. So initially in this particular diagram, how we are finding out the total heat transfer? We are finding out the total heat transfer in this particular diagram by considering the overall temperature difference divided by total thermal resistance, So in this particular initial assumption, we are finding out this particular heat transfer. So we'll get Q is equal to dt divided by RTH suffix A plus RTH suffix B plus RTH suffix C. Okay, so this is nothing but overall the total heat transfer rate in this particular case. But when we are considering that there is some contact resistance present in the wall, there are some contact resistance present in the wall, so then what will happen? What will be the diagram? Okay, so we know that the heat transfer is linear within the wall, so we'll get the straight line in a particular wall. Heat transfer profile or the temperature profile will be straight line in a particular wall. But here when it reaches to the interference point, so that particular heat will opposed by or resisted by the interference resistance. Okay, interference resistance. So which kind of resistance? Air available, the surface area available for the heat transfer is lesser than the geometrical area because of the crust and troughs or the roughness of that particular surface. Oh, okay, and the voids present between the two interference wall. Okay, so that will offer large resistance. So the temperature drop will happen at the interference point. temperature drop will happen at the interference point. So initial temperature or the wall A exit temperature is T2, and because of the interference resistance, the less amount of heat will be transferred to the next wall. Less amount of heat will be transferred to the next wall. So that temperature drop will happen at the interference. So that the temperature drop will happen at the interference. And this temperature drop, we can say that here it is shown. So the exit temperature of wall A is T2, whereas the entry temperature of wall B is T3. Okay, and this particular difference at the interface, the temperature difference at the interface will be called as a temperature drop at the interface A and B. In a similar fashion, if you consider that the exit temperature of a wall B is a T4, but the entry temperature of wall C is a T5, which is lesser than the T4. And this much amount of a temperature drop will happen at the interface because of thermal contact resistance, and this thermal contact resistance arises because the total geometry is not available for the heat. The total geometric area is not available for the heat transfer, and this total geometric area is why not available for the heat transfer? Because of a roughness of that particular wall. Okay, because of a surface roughness of that particular wall. Okay, and the formation of a crust and troughs and the voids in between two meeting parts, or we can say that in between two contact parts. Okay, getting everyone? So in this particular case, we need to determine how much contact resistance is present in between A and B phase and B and C phase. Okay, how much contact resistance is present in between A and B wall and B and C wall. Okay, so the contact resistance formula will is we can say that the contact resistance are given by RTH A suffix B is equal to contact resistance, and it is equal to the temperature drop between two faces or the two walls, that is T2 minus T3. Okay, here is T2 minus T3, that is the temperature drop at the interface between A and B. Okay, divided by Q divided by area. Okay, divided by Q divided by area. So that will provide you the thermal contact resistance between A and B wall. Similarly, the thermal contact resistance between B and C wall will be provided as T4 minus T5 divided by Q divided by area. Okay, so T4 is the exit temperature of B wall and T5 is the entry temperature of C wall. Okay, so difference between that will be temperature drop at the interface B and C. Okay, divided by Q divided by area. That will provide you the thermal contact resistance between wall B and wall C. Now, what will be the complete equation for the heat transfer in this particular case? If you are considering the thermal contact resistance, then what will be the total heat transfer rate in this particular equation, or how we can determine the total heat transfer rate if the thermal contact resistance is given quantity in the problem. So in that case, we have to use this particular formula. Okay, so this is the generalized formula for three walls and having two thermal contact resistance. Okay, so in that case you can use this formula. Q is equal to dt. Dt means what? Overall temperature difference whole divided by RTHA is the thermal resistance of A wall, whereas RTHAB is the thermal contact resistance between A and B wall, plus RTHB is the thermal resistance of a B wall, whereas RTHBC contact is the thermal contact resistance between B and C wall, and RTHC is the thermal resistance of a C wall. Okay, so let us compare the initial equation and the final equation. Initially, if you are not considering contact resistance, so in that case we have to consider the wall resistance only. Okay, we have to consider the wall resistance only. Okay, if there is no contact resistance present, in that case we have to consider only wall resistance. Okay, so RTHA, RTHB and RTHC are the resistance we can consider that because of its thickness of that particular wall. Whereas when we consider the thermal contact resistance, we have to add up the thermal contact resistance in a total resistance. So RTHA, RTHB and RTHC as it is, but we have added the interference resistance or thermal contact resistance as RTHAB contact plus RTHBC contact, that is the thermal contact resistance. Getting everyone? Whether you understood what is meant by contact resistance? Is there any doubt, any question? Okay, write down thermal contact resistance. Thermal contact resistance. Is there any question? Whether you understood or not? Shall I repeat the point? If you required the repetition, then also it is fine. No problem for me. I will repeat the point. आपको क्या समझना है? पहले तो हम अब तक क्या कर रहे थे कि थर्मल कॉन्टैक्ट रेजिस्टेंस हम कंसीडर नहीं कर रहे थे. ओके, मतलब प्रॉब्लम की स्टेटमेंट वैसी हो तो वैसे ही सॉल्व करना पड़ेगा. जब प्रॉब्लम की स्टेटमेंट में आपको थर्मल कॉन्टैक्ट रेजिस्टेंस प्रोवाइड किया होगा तब आपको वो कंसीडर करना पड़ेगा. बट जब आपको थर्मल कॉन्टैक्ट रेजिस्टेंस नहीं दिया है गिवन क्वांटिटी में, तब आपको वो कंसीडर नहीं करना है. ये डाउट आप पहले क्लियर कीजिएगा. इनिशियली हम क्या कर रहे थे, हम ये समझ रहे थे कि वॉल ए का एग्जिट टेम्परेचर जो है वो वॉल बी का एंट्री का टेम्परेचर है. ओके, T2 is the exit temperature of a wall A. Okay, and the same temperature we are considering for the wall B as a entry temperature. Okay, entry temperature. कब ये होगा? जब थर्मल कॉन्टैक्ट रेजिस्टेंस नहीं होगा तब ये होगा. बट एक्चुअल में क्या होता है? एक्चुअल में किसी भी सरफेस, कौन सा भी, कितना भी पॉलिश्ड सरफेस आप ले लो, उस पर आपको थोड़ा सा तो रफनेस मिलेगा ही. ओके, थोड़ा सा तो रफनेस मिलेगा ही. रफनेस मीन्स व्हाट? देयर आर presence of a crust and troughs. There are presence of a crust and troughs. Okay, what kind of crust? And if you see this zoomed pictures, okay, if you see this particular zoomed pictures, so these are zoomed picture by using the magnifying glasses, okay, or by using the telescopes. These are the zoom pictures. Okay, so you can see that on a plane surface also there are some crust and troughs present over there. Okay, now this particular crust and troughs, when it will be in a contact with the another surface which is also having the crust and troughs, or which is also having some different kinds of roughness. Okay, so it will connect to another surface. Then there will be some kinds of voids present in between the contact of that two particular walls. Okay, some kinds of voids means what? गैप रहता है वहां पे, छोटा छोटे गैप रहते हैं वहां पे, और उस गैप में क्या होता है? एयर ट्रैप हो जाती है. उस गैप में क्या होता है? एयर ट्रैप होती है. सो एयर क्या है? बैड कंडक्टर ऑफ हीट है. ओके, जितनी हीट मटेरियल में से ट्रांसफर होती है उसमें से बहुत कम हीट एयर से ट्रांसफर होती है. तो एयर क्या हो गया? बैड कंडक्टर ऑफ हीट हो गया. तो जो बैड कंडक्टर होता है वो ज्यादा रेजिस्टेंस प्रोवाइड करता है हीट ट्रांसफर के लिए. ओके, जो बैड कंडक्टर होता है वो ज्यादा रेजिस्टेंस प्रोवाइड करता है हीट ट्रांसफर के लिए. तो जो एग्जिट टेम्परेचर रहेगा, अब हम जब भी कंसिडर करेंगे थर्मल रेजिस्टेंस, ओके, जब भी कंसिडर करेंगे इंटरफेरेंस रेजिस्टेंस, सो इन दैट केस what will happen? Due to the crust and troughs, okay, जो एग्जिट टेम्परेचर है वॉल ए का और जो कि हीट बाहर निकल रही है वॉल ए से, उतनी ही हीट वॉल बी को नहीं मिलेगी. ओके, जितनी बाहर निकली है वॉल ए से वो हीट वॉल बी को नहीं मिलेगी. उससे थोड़ा कम हीट वॉल बी को मिलेगी. क्यों? क्योंकि यहाँ पे इंटरफेरेंस रेजिस्टेंस मिल रहा है हीट ट्रांसफर के लिए. ओके, क्योंकि यहाँ पे इंटरफेरेंस रेजिस्टेंस मिल रहा है हीट ट्रांसफर के लिए. ओके, जो एयर ट्रैप्ड है वो रेजिस्ट कर रही है हीट ट्रांसफर के लिए. सो जो टेम्परेचर वॉल बी का एंट्री लेवल का टेम्परेचर है वो वॉल ए के एग्जिट टेम्परेचर से कम रहेगा. सो यहाँ पर हमें डिफरेंस दिखाई दे रहा है. T2 is the exit temperature of wall A, whereas T3 is the entry temperature of wall B. So ये जो डिफरेंस है, ये डिफरेंस को बोलते हैं टेम्परेचर ड्रॉप एट द इंटरफेसेस between the two walls. Which are that two walls? A and B. Okay, A and B. Similar kind the thermal contact resistance will be there between the walls B and C. Okay, similar kind of a thermal contact resistance will be present between the wall B and C. Okay, so that जो जो exit temperature है B wall का वो रहेगा T4. Okay, but entry temperature C wall का क्या रहेगा? T5 रहेगा. यानी कि जितनी हीट B wall से बाहर निकल रही है उतनी हीट C wall को नहीं मिल रही है. ओके, जितनी हीट B wall से बाहर निकल रही है उतनी हीट C wall को नहीं मिल रही है. सो इसी कारण जो एंट्री टेम्परेचर है C wall का दैट इज इक्वल टू T5 वो T4 से कम रहेगा. वो T4 से कम रहेगा. गेटिंग एवरीवन? Getting everyone? So the difference between the temperatures at the interface between the two walls is called as a temperature drop at the interface. Okay, now हमें क्या करना है, अभी कितना रेजिस्टेंस है इन दोनों वॉल में वो फाइंड आउट करना है. कितना रेजिस्टेंस है इन दोनों वॉल में एट इंटरफेस वो फाइंड आउट करना है. सो उसका एक सिंपल फॉर्मूला है. वो फॉर्मूला क्या है? RTHAB, that is the thermal resistance between A and B wall, or we called it as a thermal contact resistance between A and B wall, will be equal to temperature drop at the interface between A and B. कितना टेम्परेचर ड्रॉप हो रहा है? T2 minus T3 इतना टेम्परेचर ड्रॉप हो रहा है between A and B wall. Okay, divided by heat transfer rate per unit area. ये हमें क्या देगा? कॉन्टैक्ट रेजिस्टेंस देगा, थर्मल कॉन्टैक्ट रेजिस्टेंस देगा in between A and B wall. Similarly, for B and C wall, contact resistance equal to T4 minus T5 divided by Q by A, where T4 minus T5 is the temperature drop between B and C wall. Temperature drop between B and C wall divided by Q by A, that is heat transfer rate per unit area. Getting everyone? Now in this case, if you want to find out the total heat transfer, then we have to take the fraction of total or overall heat overall temperature difference divided by addition of all the thermal resistance. Addition of all the thermal resistance. Initially हमें wall के thermal resistance थे खाली. Okay, RTHA, RTHB, RTHC ये wall के thermal resistance है. अब उनके कॉन्टैक्ट रेजिस्टेंस भी उसमें ऐड करेंगे हम. उनके कॉन्टैक्ट रेजिस्टेंस भी उनमें ऐड करेंगे हम. सो हमें टोटल हीट ट्रांसफर रेट मिल जाएगा. ओके, टोटल हीट ट्रांसफर रेट मिल जाएगा. इज देयर एनी डाउट, एनी क्वेश्चन नाउ? वेदर यू अंडरस्टूड एवरीवन? प्लीज कमेंट इन द चैट बॉक्स whether you understood or not. ग्रेट ग्रेट ग्रेट. ऐसे रिप्लाई करते रहो, मुझे भी लग जाएगा कि आप सोए नहीं हो, नहीं तो मुझे भी नींद आ जाएगी. हाँ, अच्छे बच्चे हैं. थैंक यू थैंक यू. मत सोना, लेक्चर के बीच मत सोना, बस उतना कर दो यार. हाँ, थर्मल कॉन्टैक्ट रेजिस्टेंस, राइट डाउन द हेडिंग. थर्मल कॉन्टैक्ट रेजिस्टेंस, थर्मल कॉन्टैक्ट रेजिस्टेंस. आज मैंने व्हाट्सएप ग्रुप पे भेज दिया कि मैं कॉल करूंगा, तो देखो कितने अटेंडेंस बढ़ गई. नहीं तो 30 भी स्टूडेंट डेली अटेंड नहीं करते. तो कल मैंने 5-6 लोगों को कॉल किया और थोड़ा धमकाया भी. देखता हूँ आज वो अटेंड कर रहे हैं कि नहीं. नहीं तो कल फिर आज शाम को फिर से कॉल करूंगा उनको. और मैं सीधी बात नहीं करता, मैं धमकाता हूँ सीधा. ओके, और धमकी भी ऐसी नहीं है कि बोल दिया और छोड़ दिया, मैं वैसे ही पकड़ लेता हूँ आगे जाके. ठीक है, तो अच्छे बच्चे की तरह बिहेव करो. ओके, आपने फीस दी है, आपने इतना कॉम्प्रोमाइज किया है, ये लॉकडाउन चल रहा है और आप घर बैठ के सीख रहे हो, और इससे अच्छी बात क्या हो सकती है? कोई घर का काम रहेगा तो बता देना टीचर को कि यस आई हैव सम वर्क, आई हैव दिस पर्टिकुलर प्रॉब्लम, बिकॉज ऑफ दैट आई एम नॉट अटेंडिंग दिस पर्टिकुलर लेक्चर। ओके, जो भी सीसी है, आपके प्रॉक्टर टीचर है, उनको एक मैसेज डाल देना बस। और जेन्युइन प्रॉब्लम मतलब डेली का प्रॉब्लम रहेगा ये, तो हम आप हमें बता सकते हैं, हम आपके पेरेंट्स से बात करेंगे। ओके, बट लेक्चर मिस मत करना। ओके, बिकॉज you are preparing for your future. Okay, and if you miss this, you will miss the opportunity in the future. Okay, समझ में आ रहा है? तो हम यहाँ पे राइटअप पार्ट पूरा करते हैं। थर्मल कॉन्टैक्ट रेजिस्टेंस, थर्मल कॉन्टैक्ट रेजिस्टेंस, राइट डाउन थर्मल कॉन्टैक्ट रेजिस्टेंस। in composite wall in composite wall in composite wall in composite wall, the calculation of heat flow, the calculation of heat flow in composite wall, the calculation of heat flow, the calculation of heat flow are made and assumptions, are made and assumptions, are made and assumptions, are made and assumptions, are made and assumptions. First one, the contact between adjacent layers, the contact between adjacent layers, the contact between adjacent layers is perfect, is perfect. कांटेक्ट कैसा है? हम क्या अज्यूम कर रहे हैं इनिशियली? हम अज्यूम कर रहे हैं कि कांटेक्ट परफेक्ट है, मतलब जो ए वॉल का सरफेस एरिया है, वो सभी सरफेस एरिया बी वॉल के सरफेस एरिया को कंप्लीट से मीट कर रहा है। ओके, ये हम अज्यूम कर रहे हैं इनिशियली। ओके, कांटेक्ट बिटवीन एडजेसेंट लेयर इज परफेक्ट। सेकंड वन, at the interface, at the interface, at the interface, at the interface, there is no fall of temperature, there is no fall of temperature. At the interface, there is no fall of temperature. At the interface, there is no fall of temperature. Okay, temperature fall नहीं हो रहा है, ये हम assume कर रहे हैं। Then third, at the interface, the temperature is continuous. When continuous, at the interface, temperature is continuous. At the interface, the temperature is continuous. Okay, at the interface, the temperature is continuous. ये हमने assume करके previous के problem solve किए हैं। But what is happening? There is a discontinuity in temperature gradient. Although there is a discontinuity in temperature gradient, although there is discontinuity in temperature gradient. Okay, although there is discontinuity in temperature gradient. Okay, so no need to draw this. So next, write down, in a real system, in a real system, in a real system, however, in real systems, however, due to surface roughness, due to surface roughness, due to surface roughness and void spaces, due to surface roughness and void spaces, void spaces, void spaces, in bracket usually filled with air, in bracket usually filled with air, in bracket usually filled with air, bracket complete. The contact surfaces, the contact surfaces touch only at discrete locations, touch only at discrete location. Okay, सभी सरफेस टच नहीं होगा, जितने भी क्रेस्ट रह गए उतना ही सरफेस टच होगा। ओके, समझ में आ रहा है? जितना भी चढ़ाव रहेगा उस सरफेस पे उतना ही पार्ट दूसरे सरफेस को टच करेगा। ओके, जितने क्रेस्ट रहेंगे, जितने उतार रहेंगे, क्रेस्ट रहेंगे, ओके, उतना पार्ट दूसरे सरफेस को टच नहीं रहेगा, टच नहीं हो पाएगा। ओके, सो यहाँ पे वही बोला है, द कॉन्टैक्ट सरफेसेस टच ओनली एट अ डिस्क्रीट लोकेशन। ओके, टच ओनली एट डिस्क्रीट लोकेशन, full stop. Thus 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 there is not a single plane of a contact. Okay, thus there is not a single plane of a contact. Thus there is not a single plane of contact, which means which means which means which means that which means that the area available for the flow of heat, the area available for the flow of heat at interface will be small. The area available for the flow of heat at interface will be small compared to geometric face area. Compared to geometric face area. Compared to geometric face area. Okay. Geometric face area. कम एरिया रहेगा तो क्या होगा? कम हीट फ्लो होगी. We know that heat transfer rate is directly proportional to perpendicular surface area. जब एरिया अवेलेबल फॉर द हीट ट्रांसफर कम रहेगा तो हीट ट्रांसफर रेट क्या रहेगा? कम रहेगा. ओके, सो ड्यू टू रिड्यूस्ड एरिया, ड्यू टू रिड्यूस्ड एरिया, ड्यू टू रिड्यूस्ड एरिया, due to reduced area and presence of air voids, due to reduced area and presence of air voids, comma, a large resistance, air voids, a large resistance to heat flow, to heat flow, large resistance to heat flow at the interface occurs. Due to reduced area and presence of air voids, a large resistance to heat flow at the interface occurs. At the interface occurs. This resistance is known as thermal contact resistance. This resistance is known as thermal contact resistance, and it causes temperature drop, and it causes temperature drop, and it causes temperature drop. Getting everyone? Understood the theory part? Now write down, draw this particular diagram. Everyone draw this diagram. Show the temperature drop at the interfaces by showing the entry level, exit level temperature uh, for the wall A different one than the exit entry level temperature for wall B. Exit level temperature for wall A is different than or greater than the entry level temperature of wall B. Okay, and similarly the exit level temperature of wall B is T4, which is greater than the entry level temperature of wall C. Okay, and the difference between these two temperatures at the interface T2 minus T3 will be called as a temperature drop at the particular interface, that is interface AB. And similarly T4 minus T5 is the temperature drop at the interface B and C. Okay, quickly draw this diagram. I will give 2 minutes. Okay, have you drawn the diagram? Shall we move ahead? Now, the contact resistance are given by the contact resistances are given by the contact resistances are given by contact resistance are given by RTH R suffix TH AB bracket complete contact. So in short form write down. So it should be suffix one only. CONT dot. Okay. RTH AB bracket complete contact is equal to T2 minus T3 T2 minus T3 whole divided by Q by A whole divided by Q by A. So can you tell me what will be its unit? What will be its unit? Contact resistance unit? What will be its unit? So temperature unit is degree Celsius. Then heat transfer rate Q unit is watt and area unit is meter square. So it will be degree Celsius per unit watt per unit area. Okay, per unit watt per unit area. Degree Celsius per unit watt per unit area. That will be the unit for thermal contact resistance. Okay, so RTH BC contact is equal to T4 minus T5 divided by Q by A. Divided by Q by A. Okay, so Q is equal to, if you want to determine the heat transfer rate when the contact resistance is provided to you, so in that case we have to add up the contact resistance in a total resistance. Okay, whatever the resistance we are calculating, we have to add up that particular contact resistance also in the resistance. Okay, so Q is equal to dt divided by RTHA, that is the wall A thermal resistance, then RTHAB contact, that is the contact resistance between A and B wall, plus RTHB is the wall resistance, wall thermal resistance of wall B, then RTHBC contact is the contact thermal resistance between the wall B and C, and plus C wall thermal resistance is RTH suffix C. Okay. Getting everyone? Is there any doubt, any question? Okay, if you don't have any doubt, then we will move ahead to the problem on this particular point. Okay, write down problem number 4. Problem number 4. Problem number 4. Everybody write down. A wall of furnace, a wall of furnace a wall of furnace is made up of a wall of furnace is made up of inside layer of silica brick inside layer of silica brick 120 mm thick, 120 mm thick, inside layer of silica brick 120 mm thick, covered with covered with covered with magnetite magnetite brick, covered with magnetite brick 240 mm 240 mm thick, covered with magnetite brick 240 mm thick, full stop. The temperature at the inside surface of silica brick, the temperature at the inside surface of silica brick, the temperature at the inside surface of silica brick wall and outside surface of magnetic brick wall, magnetite brick wall, magnetite brick wall, surface of magnetite brick wall are 725 degrees Celsius, 725 degrees Celsius and 110 degrees Celsius and 110 degrees Celsius, 110 degrees Celsius, full stop. 110 degrees Celsius, full stop. The contact thermal resistance, the contact thermal resistance between two walls, the contact thermal resistance between two walls at the interface is is 0.0035 degrees Celsius per watt, 0.0035 degrees Celsius per watt per unit wall area, per unit wall area, per unit wall area, full stop. If thermal conductivity of silica, if thermal conductivity of silica and magnetite brick and magnetite brick are 1.7 watt, 1.7 watt per meter degree Celsius, 1.7 watt per meter degree Celsius, 1.7 watt per meter degree Celsius and 5.8 and 5.8 watt and 5.8 watt per meter degree Celsius, per meter degree Celsius. Then calculate first one, the rate of heat loss, the rate of heat loss per unit area of wall, the rate of heat loss per unit area of wall, the rate of heat loss per unit area of wall. And second one, the temperature drop at the interface, the temperature drop at the interface. Okay, so in general I will describe the problem. Two walls are there, okay, which are connected to each other. One is silica wall and another one is the magnetite wall. Okay, silica wall thickness is 120 mm and magnetite wall is having thickness of 240 mm. Okay, so then next, in the given data, the temperature or the surface temperature of silica wall and magnetite wall are provided, and it is equal to 725 and 110 degrees Celsius. Okay, then they have mentioned that the thermal resistance is present, thermal contact resistance is present in between two walls. Okay, and because of that the temperature drop will happen. Okay, and it is provided as 0.0035 degrees Celsius per watt per unit area of wall surface. Okay, and also they have provided the thermal conductivities of magnetite and silica wall. Okay, magnetite and silica wall. Now we have to calculate the rate of heat loss per unit area of wall and the temperature drop at the interface. Okay, these two things we have to determine. Okay, so initially we have to draw the diagram according to the data. We have to draw the diagram. Okay, so diagram will be in a such a manner. First, wall A is the silica brick wall, and whose surface is maintained at a 725 degrees Celsius. Okay, as per the given data, and there is a the temperature drop or the thermal contact resistance between the two walls. Okay, and wall B is the magnetic brick wall. Okay, and this temperature drop, exit temperature of wall A is T2, whereas the entry temperature of wall B is the T3. Now exit temperature of wall B is provided. Okay, that is the, here in the problem it is provided that the temperature at the inside surface of silica brick wall and outside. Inside surface means what? This is the inside surface for the silica wall, and outside surface of magnetic brick is, this is the outside surface of magnetic brick, and it is provided as 110 degrees Celsius. So T4 is provided. Okay, T4 is provided. Now the thicknesses are provided. We have to put up the thicknesses, and we have drawn one we have considered only one dimensional heat flow. So draw it 2D diagram. Okay, so LA is equal to, L suffix A is equal to 120 mm, and whereas L suffix B is equal to 240 mm. These are the thicknesses. So write down the given data. L suffix A is equal to 120 mm. L suffix A is equal to 120 mm, which is equal to 0.120 meter, which is equal to 0.120 meter, and L suffix B is equal to 240 mm, which is equal to 0.240 meter. L suffix B is equal to 240 mm, and which is equal to 0.240 meter. Then T1 is equal to 725 degrees Celsius. T1 is equal to 725 degrees Celsius, and T2 is equal to, T4 is equal to, so T4 is equal to 110 degrees Celsius. T4 is equal to 110 degrees Celsius. Then thermal conductivity of silica brick, that is K suffix A is equal to 1.7 watt per meter degree Celsius. 1.7 watt per meter degree Celsius. And thermal conductivity of magnetite brick is K suffix B is equal to 5.8 watt per meter degree Celsius. 5.8 watt per meter degree Celsius. Then thermal contact resistance between A and B is R suffix TH bracket complete suffix contact CONT dot is equal to 0.0035 degrees Celsius per watt per unit area. Degrees Celsius per watt per unit area. And what we have to find out? Heat transfer rate per unit area. Okay, first one is heat transfer rate per unit area, or heat loss per unit area we need to find out. So that is Q divided by A, which is nothing but heat flux. Q divided by A is nothing but heat flux, which is equal to small q. Okay, that we have to find out first. And then second, temperature drop at the interface. Temperature drop at the interface. Okay, so that we have to find out. That is nothing but T2 minus T3. This is the temperature drop at the interface that we have to find out. Okay, so these two are the unknown quantities. Okay, so our solution, first we have to determine the rate of heat loss per unit area. We know that it is equal to overall temperature difference divided by all the summation of all the thermal resistance. Okay, Q is equal to dt divided by summation of R suffix th. Okay, so we know that. So wall A is having its own thermal resistance. Okay, wall B is having its own thermal resistance. Okay, so two thermal resistance for the walls and one thermal resistance for the contact, one thermal resistance of contact. Okay, or the contact thermal resistance. So total resistance are equal to 3. Okay, total number of resistance are equal to 3. Okay, so our equation will be Q is equal to overall temperature difference dt whole divided by RTH suffix A plus RTH suffix AB contact plus RTH suffix B. Okay, getting everyone? How we have to modify the equation depending on our data. So Q is equal to dt divided by dt divided by RTH A, RTH B, AB contact plus RTH B. Okay. So in this manner, we have to modify the equation. Write down the equation. Okay. Further, we have to determine rate of heat loss per unit area. Okay. So we need to put up the formulas for RTH A, RTH AB, and RTH B. Okay. So RTH A, that is the thermal resistance of wall A, is nothing but L suffix A divided by K suffix A multiplied by area. Okay. L suffix A divided by K suffix A multiplied by area. Plus, now contact resistance value is provided. So we have to keep as it is, RTH AB contact. Okay. Directly they have provided the value. So no need to calculate once again this particular contact resistance. So value is provided. So keep as it is. Plus plus wall resistance of wall B. Okay. Thermal resistance of wall B. And it is equal to L suffix B divided by K suffix B multiply by area. Okay. So further, we have to determine what? We have to determine heat transfer rate per unit area. So for that purpose, we have to take common 1 upon A common from the denominator, and we have to shift that 1 upon A to the numerator side. Okay. We have taken common from the denominator 1 upon A. Okay. So here in the contact resistance is already provided as degrees Celsius per watt per unit area. Okay. So that we can take directly common A, 1 upon A, that is 1 upon area, we can take common and we can shift 1 upon A to the numerator. Okay. 1 upon A in the denominator, it is equal to if we take the common, and if you want to shift it, if you want to shift that to the numerator, then it will be multiplied with the numerator. Okay. So 1 upon A we have taken common from the denominator, and once area will be shifted to the numerator side. Okay. Getting everyone? Now this is the simple conversion of equation. So now if you taken the 1 upon A common and shifted to the numerator side, then shift that area on the opposite side. Okay. You shift that area on the opposite side. So it will becomes Q divided by area, or heat transfer rate divided by area, which is nothing but heat flux. So that we have written small q, it represents the heat flux, heat transfer rate per unit area, which is equal to dt is nothing but what? Overall temperature difference. So here once again in the diagram, what is the initial temperature? T1 is the initial temperature and the final temperature is T4. So difference between these two temperatures will provide you the overall temperature difference. So we have written over here T1 minus T4 as a overall temperature difference. Okay, and we have kept other terms as it is. Okay, we have kept other terms as it is. Okay, so then just put up the values T1, T4, LA, KA, L suffix B, K suffix B, and RTH AB contact, and find out the heat transfer rate per unit area or heat flux. Okay, do calculation everyone. And put up your answer in the chat box. I request roll number 35, 77, and 25. You reply your answers in the chat box. Compulsory for roll number 35, 77, and what is the last number I have taken? 25. Okay, and others also you can reply. So Projwal has given the answer. Check whether you are getting the same answer or not. Everyone check that whether you are getting the 35 also given the answer. $55 also given the answer. 25 also given the answer. Okay, I'll check my answer. So my answer is somewhat different than you. Okay, but 35 answer is matching with my answer. 25 answer. Okay, roll number 25 answer matching with my answer, and 5 it is equal to 5324.67. Okay, and its unit will be watt per meter square. Okay, watt per meter square. Check whether you are getting the same answer. Okay, everybody calculated. Okay, so next our second unknown, that is nothing but we have to determine the temperature drop at the interface. Okay, temperature drop at the interface, that is nothing but T2 minus T3 we have to determine. And to determine this value we have to use the important concept, that is nothing but what? The overall heat transfer through the composite wall is equal to the heat transfer through individual walls of composite wall. Okay, individual walls of composite wall. Okay, overall heat transfer through the complete or throughout the wall, complete composite wall is equal to heat transfer through individual walls of that particular composite wall, individual walls of a composite wall. Okay, so as the same heat flows, through each layer of a composite wall, write down the statement: as the same heat flows through each layer of composite wall, therefore q is equal to small q is equal to that is heat transfer rate per unit area. Small q means what? heat transfer rate per unit area, capital Q divided by area, which is equal to T1 minus T2, which is equal to T1 minus T2 whole divided by L suffix A divided by K suffix A, and it is also equal to T3 minus T4. It is also equal to T3 minus T4 divided by L suffix B divided by K suffix B. Okay, T3 minus T4 whole divided by L suffix B divided by K suffix B. Okay, by using this particular equation, we have to determine the values of T2 and T3, and then we have to determine the temperature drop. Okay, so consider first equation, that Q is equal to T1 minus T2 divided by L suffix A divided by K suffix A, and find out the unknown quantity T2. Okay, so Q is equal to T1 minus T2 whole divided by L suffix A divided by K suffix A. Okay, just now only we have find out the Q value. Okay, small q value, that is heat transfer rate per unit area. Heat transfer rate per unit area. So just take that value 5324 T1 is the given quantity. T1 is the given quantity. It is equal to 725, and T2 we need to determine. Okay, T2 we need to determine. So 725 minus T2. LA, that is the L suffix A is the thickness of wall A, and it is equal to 0.12, and K suffix A is the thermal conductivity of wall A, and it is equal to 1.7. Just put up the values and find out T2. Find out T2, that is the temperature at the exit of wall A. Find out the T2 value. In a similar fashion, Q is equal to T3 minus T4 divided by whole divided by L suffix B divided by K suffix B. Q is known, T4 is known, L suffix B and K suffix B are known. Just find out T3 value. Okay, unknown is T3 only. Find out T3 value. Please let me know what is T2, how much you are getting. Okay, T2 349.14, T3 330.33. Okay, 349. Yash Nihal has given the answers. Others also, please do calculation. Whether others are getting the same values. Okay, I will check my value. Okay, so T2 I'm getting 349.14 degrees Celsius. Okay, now here how to write a degree Celsius. (349.14 degrees Celsius). Okay, so that is T2, and T3 330 0.33 degree Celsius. Okay, these are our answers. And determine the temperature drop at the interface. Okay, determine the temperature drop at the interface. How much it is? T2 minus T3. It will be equal to 18.81 degree Celsius. Okay, temperature drop at the interface will be equal to T2 minus T3 equal to 18.81. Everybody getting these answers? You should be correct up to first decimal, no problem. Okay, if you are correct up to first decimal, then no problem. Whether you are getting the same answers or not, whether you understood, please let me know in the chat box how to solve the problems on thermal contact resistance. Getting idea? Okay, great, great. Shall I move ahead for the next point? Okay. Now our next point is, write down the heading as the overall heat transfer coefficient. Overall heat transfer coefficient. Overall heat transfer coefficient.
Hello, sir.
Yes.
I have one problem, sir.
Please ask.
सर तुम्ही तिथं एरिया कॉमन बाहेर काढलाय का ना, तिथं प्रॉब्लेम आहे सर.
बर एरिया कॉमन बाहेर काढला. ओके, कुठून? इथं. ओके.
हा, इथून.
ह्यात काय ह्याचं ना कॉन्टॅक्ट रेजिस्टन्स. बरोबर ना, कॉन्टॅक्ट रेजिस्टन्सचा एरिया कसा काय घेतला मी? ह्यात तर कुठे टर्म दिसत नाही एरियाची, तरी पण कसा काय बाहेर घेतला? राईट ना, हाच क्वेश्चन असेल. नाव आता इथं लक्ष दे. गिवन क्वांटिटी मध्ये आपल्याला कॉन्टॅक्ट रेजिस्टन्सची व्हॅल्यू दिलेली आहे. ठीक आहे, किती दिलेली आहे? 0.0035 डिग्री सेल्सिअस. ओके, डिग्री सेल्सिअस वॅट पर युनिट एरिया दिलेला आहे. येते लक्षात? समजला तुला? ही जी व्हॅल्यू आहे तीच व्हॅल्यू आपल्याला डिग्री सेल्सिअस पर वॅट पर युनिट एरिया मध्ये दिलेली आहे. येते लक्षात? त्यामुळे तिथे एरिया ऑटोमॅटिक येणारच. ओके, इथे एरिया 1/A ऑटोमॅटिक येणारच. समजतंय का? सो दॅट वी कॅन टेक कॉमन without disturbing this particular second term, we can take 1/A common from entire bracket because this is the value only. Okay, and its unit is per unit area. Getting? So that we can take common from here. Okay, we can take common from here as we have taken common for this bracket and this bracket. Okay, area. So we can take directly common from here because the value is provided in a degree Celsius per unit watt per unit area. Okay, so we can take common and we can shift it to the numerator side. Okay, so that is the mathematical operation. Okay, if you are considering this, so here if you are considering this, then we can say that out of bracket 1 divided by area. Okay, bracket complete. Now if you want to shift this to the numerator, okay, 1/A कॉमन काढल्यानंतर आपण जर हे शिफ्ट न्यूमरेटरला करायचं असेल तर आपण काय करतो? इथं मल्टिप्लाय बाय करतो. मल्टिप्लाय बाय. ओके, मग हे काय होतं? A डिवायडेड बाय 1 होतं. राईट ना? आणि इथून हे निघलं जातं. हे मॅथमॅटिकल ऑपरेशन आहे. ओके, म्हणजे A काय झालं? न्यूमरेटरला मल्टिप्लाय झालं. राईट ना?
हो.
आणि पुढे काय केलंय आपण? आपल्याला काय पाहिजे? हीट ट्रान्सफर रेट पर युनिट एरिया पाहिजे. तर आपण दोन्ही साईडला जर तुम्ही जर असं म्हणत असाल की दोन्ही साईडला आपण एरियानं डिवाइड केलं, किंवा मी असं म्हणतो की एरिया जो न्यूमरेटरला आहे तो दुसऱ्या साईडला शिफ्ट केला आपण, तर तो काय झाला, डिवाइडला जाणार तो, राईट ना. दोन्ही पण ऑपरेशन, दोन्ही पण बरोबर आहे की आपण एरियानं थ्रू आउट डिवाइड केलं, किंवा मी म्हणतो असं की एरिया दुसऱ्या साईडला अपोजिट साईडला ट्रान्सफर केला, तर तो काय झाला 1/a झाला, म्हणजेच काय झाला क्यू डिवायडेड बाय एरिया झाला, राईट ना. इक्वल टू क्यू. ओके,
थँक्यू सर.
ओके. Is there any doubt, any question? Okay, so we'll move ahead to the next point, that is the overall heat transfer coefficient. Write down the heading, the overall heat transfer coefficient. The overall heat transfer coefficient. The overall heat transfer coefficient. Okay. Now, first of all, we try to understand this particular diagram, and then we'll move ahead to the concept. Okay. So diagram, what it represents. Okay. So first of all, there is one metal wall. Okay. And we can see the thickness of that particular metal wall. So this is the thickness of one metal wall. Okay. And this wall is having thermal conductivity of a K. Okay. And on one side of a wall, we are transferring the hot fluid. Okay. On one side of a wall, we are transferring the hot fluid. Okay. Now this hot fluid having a convective heat transfer coefficient of H suffix HF. Okay. So H is, small h is heat transfer coefficient. Okay. And we are using it for hot fluid, so that we are providing the suffix as HF. Okay. We are using it for the hot fluid, so that we are providing the suffix of HF. Okay. Now this hot fluid, from one side we are transferring the hot fluid, and its convective heat transfer coefficient is H suffix HF. Okay. Convective heat transfer coefficient of a hot fluid. Okay. Now the temperature of this particular hot fluid, we have to consider it as a T suffix HF, temperature of a hot fluid. Okay. Temperature of this particular hot fluid we have to consider as a T suffix HF. Now from the other side of that particular metal wall, we are transferring the cold fluid. Okay. From the other side of a metal wall, we are transferring the cold fluid. The temperature of that particular cold fluid is T suffix Cf. Temperature of cold fluid is T suffix Cf. Whereas the convective heat transfer coefficient, okay, the convective heat transfer coefficient of a cold fluid is H suffix Cf. Okay. The convective heat transfer coefficient of cold fluid is H suffix Cf. Okay. Now the wall thickness is L. Okay. Wall thickness is L. Okay. So this is the figure. Now what is changed here? Up till now, we are considering that the heat transfer through the solid body or solid wall only. Okay. We are not considering any presence of a fluid. Okay. We are not considering any presence of fluid up till now. Now here, in this particular concept, we have to consider the heat transfer from fluid to the solid surface and solid surface to the fluid. Now hot fluid is flowing through this side. Okay. And the temperature T suffix HF of that particular hot fluid is greater than the wall temperature, so that this particular fluid will transfer the heat to the wall. Okay. This particular fluid will transfer the heat to the wall. Now this heat transfer will be considered as a convection heat transfer, convection mode of heat transfer. This particular heat transfer will be considered as convection mode of heat transfer, or heat transfer. Which heat transfer mode is there? If the fluid is transferring heat to the solid surface or to the material then that particular heat transfer mode is considered as convective heat transfer. Then that particular heat transfer mode is considered as a convective heat transfer. So this particular fluid is transfer the heat to this particular wall by convection. Okay, by convection. Now once the heat will reach to this particular wall surface, okay, this particular wall surface, then this wall surface is also the heat will transfer through one side of a wall surface towards another side. Okay, from one side of a wall surface towards another side. Now this complete heat transfer will happen in a solid. Okay, this complete heat transfer will happen in a material or in a wall, so that this heat transfer in a wall will be considered as a conduction heat transfer. Okay, up till now we have discussed that only. When the heat is transferring through the solid, then that will be considered as a conduction mode of a heat transfer. Now further, when that particular heat will reach to another surface of wall, okay, when that heat is reached to another surface of wall, now the another surface wall temperature is T2. Okay, another temperature wall, another surface temperature of a wall having temperature T2, now which is greater than the cold fluid temperature, which is greater than the cold fluid temperature. Cold fluid temperature is T suffix Cf, okay, which is lesser than the T2 temperature. Okay, so that this particular wall surface, another wall surface, will transfer the heat to the cold fluid. This particular another surface of a wall will transfer the heat to the cold fluid. Once again, if the heat is transforming from the substance to the fluid, or we can say that from material or from solid surface to the fluid, then that particular heat transfer mode is convection heat transfer. Okay, that particular heat transfer mode is a convection heat transfer. Okay, समझ में आ रहा है सबको? यहाँ पे क्या हो रहा है, एक साइड से एक मेटल वॉल है, उसकी थर्मल कंडक्टिविटी K है. ओके, उस मेटल वॉल के वन साइड से हम हॉट फ्लूइड ट्रांसफर कर रहे हैं और दूसरी साइड से हम कोल्ड फ्लूइड ट्रांसफर कर रहे हैं. ओके, सो हॉट फ्लूइड से हीट क्या होगी, फर्स्ट वॉल सरफेस को ट्रांसफर होगी. ओके, हॉट फ्लूइड से हीट क्या होगी, फर्स्ट वॉल सरफेस को, और जो भी सरफेस उस हॉट फ्लूइड के कांटेक्ट में है उसको ट्रांसफर होगी. ओके, सो that particular mode of heat transfer will be considered as a convection heat transfer, because heat is transforming from fluid to the surface. जब फ्लूइड से सरफेस को हीट ट्रांसफर होती है, तब हम बोलेंगे वो मोड, हीट ट्रांसफर होने का मोड कौन सा है, कन्वेक्शन मोड ऑफ हीट ट्रांसफर. ओके, नाउ नेक्स्ट, अब हीट इस सरफेस पे पहुंच गई है. ओके, अब क्या होगी, वो वॉल के थिकनेस से ट्रांसफर होगी. ओके, अब हीट क्या होगी, वॉल के थिकनेस से ट्रांसफर होगी. अब यहाँ पे क्या कंसीडर करेंगे, वो कौन सा मोड है हीट ट्रांसफर का, वो कंडक्शन मोड है हीट ट्रांसफर का. ओके, सो नेक्स्ट, अब हीट वॉल के दूसरे छोर पर पहुंच गई है और दूसरे सरफेस पर पहुंच गई है. अब इसके बाद और एक फ्लूइड है, वो कोल्ड फ्लूइड है और उसका टेम्परेचर वॉल के दूसरे सरफेस से कम है. तो वॉल का दूसरा सरफेस उस कोल्ड फ्लूइड को हीट ट्रांसफर करेगा. यहाँ पे भी हीट सरफेस से फ्लूइड को ट्रांसफर हो रही है. जब हीट सरफेस से फ्लूइड को ट्रांसफर होती है, तब हम उस हीट ट्रांसफर मोड को क्या बोलेंगे, कन्वेक्शन मोड ऑफ हीट ट्रांसफर बोलेंगे. ओके, फ्लूइड से सरफेस को और सरफेस से फ्लूइड को हीट ट्रांसफर होती है, तब कन्वेक्शन मोड होता है हीट ट्रांसफर होने का. तब कन्वेक्शन मोड होता है हीट ट्रांसफर का होने का. ओके, और जब हीट मटेरियल विद इन अ सेम मटेरियल ट्रांसफर होती है, तब वो कंडक्शन मोड होता है. और सिंपल भाषा में बोले तो जब हीट सॉलिड में ही ट्रांसफर होती है, ओके, सॉलिड में ही ट्रांसफर होती है, तब उसको हमें प्योर कंडक्शन मोड बोलना चाहिए. ओके, जब हीट सॉलिड में ही ट्रांसफर होती है, तब उसको हम प्योर कंडक्शन मोड कहना चाहिए. ओके, गेटिंग एवरीवन? नाउ जब हम कन्वेक्शन मोड कहेंगे, तब हमें दूसरा लॉ यूज करने पड़ेगा. ओके वो कौन सा लॉ है? न्यूटन्स लॉ ऑफ कूलिंग। ओके कन्वेक्शन का कौन सा लॉ है? न्यूटन्स लॉ ऑफ कूलिंग। और एंड वो क्या स्टेट करता है? सो Q इज इक्वल टू H मल्टीप्लाई बाय A मल्टीप्लाई बाय dt और टेम्परेचर डिफरेंस बिटवीन द surface and fluid. Okay, so heat transfer rate per unit area is directly proportional to temperature difference between the surface and fluid, or between the fluid and surface. Okay, this is the law of Newton's law of cooling, which we have to apply while dealing with convection mode of heat transfer. Okay, which we have to apply while dealing with convection mode of heat transfer. Getting everyone? Now अब इन सब के रेजिस्टेंस भी हो गए, हीट ट्रांसफर हो रही है तो कुछ ना कुछ उसको अपोज भी करेगा हीट ट्रांसफर के लिए, तो इन सब के रेजिस्टेंस भी हो गए। जब हीट फ्लूइड से सॉलिड को ट्रांसफर हो रही है तो उसमें कन्वेक्शन मोड है तो उसका रेजिस्टेंस भी होगा, और जब हीट विद इन द सब्सटेंस और विद इन द मटेरियल ट्रांसफर हो रही है वो कन्वेक्शन मोड होगा, उसका भी कोई रेजिस्टेंस होगा। और जब फ्लूइड हीट सरफेस से फ्लूइड को ट्रांसफर हुई है तब उसका भी कौन सा तो रेजिस्टेंस होगा, उस हीट ट्रांसफर को कुछ तो अपोज करेगा। ओके सो ये तीन रेजिस्टेंस हमें कंसीडर करने पड़ेंगे। ओके सो इफ यू वांट टू ड्रॉ the circuit diagram for this particular geometry, then it will be represented as it is. Okay, so initial temperature for the hot fluid is T suffix HF. Now heat is transforming from this particular hot fluid to the wall surface, then that will be the convection mode of heat transfer, and the resistance for the convection mode of heat transfer will be represented as 1 divided by H suffix HF multiplied by area. Okay, that we have discussed in the convection only. Okay, how to determine the resistance of a convection by using the simple law of Newton's law of cooling, we can determine that. Okay, so then यहाँ पे नेक्स्ट टेम्परेचर क्या है? T1 डिग्री सेल्सियस है। ओके जो कि वॉल के हॉट फ्लूइड साइड का टेम्परेचर है। ओके देन वॉल का हॉट फ्लूइड साइड का टेम्परेचर है। देन हीट क्या हो रही है? विद इन वॉल ट्रांसफर हो रही है तो वो कंडक्शन मोड ऑफ हीट ट्रांसफर है। तो कंडक्शन का रेजिस्टेंस क्या होता है? थिकनेस डिवाइडेड बाय थर्मल कंडक्टिविटी मल्टीप्लाई बाय एरिया। सो यहाँ पे हमने वही लिखा है, रेजिस्टेंस ऑफ कंडक्शन that is L divided by K multiplied by area. Now next वॉल के दूसरे सरफेस से हीट कोल्ड फ्लूइड को ट्रांसफर हो रही है, वो न्यूटन्स लॉ ऑफ कूलिंग से हम रेजिस्टेंस फाइंड आउट कर सकते हैं। वो कितना है? 1 अपॉन HCF मल्टीप्लाई बाय एरिया। यहाँ पे H सफिक्स HF एंड H सफिक्स CF ये दोनों क्या है? कन्वेक्टिव हीट ट्रांसफर कोएफिशिएंट है। ओके कन्वेक्टिव हीट ट्रांसफर कोएफिशिएंट है जो कि कांस्टेंट हमने किसमें कंसीडर किया था? न्यूटन्स लॉ ऑफ कूलिंग में कंसीडर किया था। न्यूटन्स लॉ ऑफ कूलिंग क्या है? Q इज इक्वल टू H मल्टीप्लाई बाय एरिया मल्टीप्लाई बाय टेम्परेचर डिफरेंस बिटवीन सरफेस एंड फ्लूइड। ओके वो न्यूटन्स लॉ ऑफ कूलिंग है। ओके गेटिंग? सबको समझ में आया क्या है डायग्राम? नाउ हमें क्या करना है? सो यहाँ पे जब भी हम इस टाइप के ज्योमेट्री को डील करते हैं तब हमें ओवरऑल हीट ट्रांसफर कोएफिशिएंट की जरूरत पड़ती है, और तब हमें ओवरऑल हीट ट्रांसफर कोएफिशिएंट फाइंड आउट करना पड़ता है। ओके सो व्हाइल डीलिंग विद द प्रॉब्लम्स ऑफ अ फ्लूइड टू फ्लूइड हीट ट्रांसफर across a metal boundary, it is usual to adapt an overall heat transfer coefficient which is denoted as capital U, which gives the heat transmitted per unit area, per unit time, per degree temperature difference between the bulk fluid on each side of a metal. Okay, so now ये कैसे डिटरमाइन करना है? ये हमें खाली न्यूटन्स लॉ ऑफ कूलिंग से और फोरियर लॉ से ही डिटरमाइन करना है। नाउ we can represent the equations for the flow of the heat in this particular manner. So heat flow equations will be, so first क्या है? हीट कहां से कहां ट्रांसफर हो रही है? हॉट फ्लूइड से इस सरफेस को हीट ट्रांसफर हो रही है। ओके हॉट फ्लूइड से इस सरफेस को हीट ट्रांसफर हो रही है। वो कौन सा मोड है हीट ट्रांसफर का? कन्वेक्शन मोड है हीट ट्रांसफर का। सो हमें फर्स्ट वी हैव टू कंसीडर हीट ट्रांसफर between hot fluid and wall surface. Okay, heat transfer between hot fluid and wall surface is a convection heat transfer. Is a convection heat transfer. So यहाँ पे मैं लिखता हूं according to Newton's law of cooling, according to Newton's law of cooling, we can write Q is equal to ये क्या लॉ है? लॉ का स्टेटमेंट क्या है? हीट ट्रांसफर पर यूनिट एरिया इज डायरेक्टली प्रोपोर्शनल टू टेम्परेचर डिफरेंस बिटवीन सरफेस टेम्परेचर एंड द फ्लूइड टेम्परेचर. सरफेस टेम्परेचर एंड द फ्लूइड टेम्परेचर. सिंपल लॉ है. और उसका मैथमेटिकल स्टेटमेंट क्या है? Q इज इक्वल टू H मल्टीप्लाई बाय A मल्टीप्लाई बाय dt. ओके, वो मैथमेटिकल स्टेटमेंट है. सो यहाँ पे हमें ये लॉ किसके लिए यूज करना है? यहाँ पे हमें ये लॉ जब हीट हॉट फ्लूइड से मेटल सरफेस को ट्रांसफर हो रही है तब हमें ये लॉ यूज करना है यहाँ पे. ओके, सो हमने यूज किया लॉ Q इज इक्वल टू हीट ट्रांसफर कोएफिशिएंट क्या है हॉट फ्लूइड का? H सफिक्स HF है. ओके, एरिया कितना है? कैपिटल A है. मल्टीप्लाई बाय हॉट फ्लूइड का टेम्परेचर कितना है? T सफिक्स HF है. माइनस उस साइड के वॉल सरफेस का टेम्परेचर क्या है? T1 है. उस साइड के वॉल टेम्परेचर का वॉल सरफेस का टेम्परेचर क्या है? T1 है. सो we will get the equation as Q is equal to H suffix HF multiply by area multiply by into bracket T suffix HF minus 1. So ये हमारा equation number 1 हो गया. Now we have to rearrange this equation in the form of a temperature difference. We have to rearrange this equation in the form of a temperature difference. So we have converted this equation in the form of a temperature difference. Okay, how we have converted? We have kept temperature difference as it is. Remaining terms we have shifted to another side. So it will become T suffix HF minus T1 will be equal to Q divided by H suffix HF multiply by area. Q divided by H suffix HF multiply by area. Okay, so next क्या हो रहा है? अब हमें हीट कन्वेक्शन मोड से ट्रांसफर होके इस वॉल के सरफेस तक पहुंच गई. ओके, नाउ हीट क्या होगी? इस वॉल में ट्रांसफर होगी. जब वॉल में हीट ट्रांसफर होगी तो वो क्या होगा? कंडक्शन मोड होगा हीट ट्रांसफर का. सो हमें नेक्स्ट हीट ट्रांसफर का मोड कंसीडर करना है. नेक्स्ट हमें क्या करना है? हीट ट्रांसफर विद इन द मेटल वॉल is conduction heat transfer. Heat transfer within the metal wall is conduction heat transfer. So यहाँ पे हमें क्या करना है? According to Fourier's law. Okay, conduction का कौन सा लॉ है? Fourier's law. According to the Fourier's law. So according to Fourier's law, we can write the equation as Q is equal to K multiply by area multiply by T1 minus T2 divided by L, whereas K is the thermal conductivity of that particular wall, A is the area, perpendicular surface area for the heat transfer, T1 minus T2 is the temperature difference between the two surfaces, and whole divided by L is the thickness of that particular wall. Okay, so this is our Fourier's law we have applied for the heat transfer within the metal wall. Then next we have to convert this equation in the form of a temperature difference, so that we have kept the T1 minus T2 on one side and remaining part or remaining terms we have shifted to another side. So we will get the equation as T1 minus T2 is equal to Q multiply by L divided by K multiply by A. Okay, T1 minus T2 is equal to Q multiply by L divided by K multiply by A. So that will be our equation number 4. Now हम कहाँ तक पहुंचे? ओके, हम यहाँ तक पहुंचे, दूसरे सरफेस तक पहुंचे. अब इस दूसरे सरफेस से हीट कोल्ड फ्लूइड को ट्रांसफर हो रही है. अब इस दूसरे सरफेस से हीट, नाउ हियर द हीट इज ट्रांसफरिंग फ्रॉम सेकंड सरफेस ऑफ अ वॉल to the cold surface. Okay, to the cold surface. Now here the temperature of surface of a wall is greater than the cold fluid temperature, so that heat will transfer from the wall surface to the cold fluid. Okay, so now this mode of heat transfer will be considered as a convection heat transfer. So once again we have to apply the Newton's law of cooling to determine the heat transfer rate. We have to apply the Newton's law of cooling to determine the heat transfer rate. Okay, so once again we have applied we have considered the heat transfer from metal wall surface to cold fluid. Okay, heat transfer from metal wall surface to cold fluid. Now this heat transfer is convection heat transfer. Okay, it's convection heat transfer. So once again we have applied the Newton's law of cooling to determine the heat transfer rate. Okay, to determine the heat transfer rate. So our equation will be Q is equal to H suffix Cf multiplied by area multiplied by temperature difference between the surface and the fluid. So surface temperature is T2, and whereas the fluid temperature is T suffix Cf, that is the cold fluid temperature. Okay, so next we have to convert this equation in the form of a temperature difference, so that we have kept this T2 minus T suffix Cf on one side, and remaining part we have shifted towards the left side. Okay, so that we will get the equation T2 minus T suffix Cf equal to Q divided by H suffix Cf multiplied by area. Okay, so that will be our equation number 6. Okay, getting everyone? Now we have to add this three equation, that is equation number 2, equation number 4 and equation number 6. We have to add this particular three equation. So adding equation 2, 4, 6. Okay, adding equation 2, 4, 6, what we will get? The addition in a such a manner that all the temperatures should be added on one side, and the or left hand side should be added on a left hand side, and a right hand side should be added on a right hand side. Okay, so in this manner if you add this, so we will get the equation as T suffix Hf minus T1 plus T suffix 1 minus T suffix 2 plus T suffix 2 minus T suffix Cf will be equal to Q divided by H suffix Hf multiplied by area plus Q multiplied by L divided by K multiplied by A plus Q divided by H suffix Cf multiplied by area. Okay, now here minus T1 is there and plus T1 is there. So minus T1 plus T1 will be cancelled. Then minus T2 is there, plus T2 is there. So minus T2 plus T2 will be cancelled. So remaining thing only in a temperature sense, remaining thing is only T suffix Hf and minus T suffix Cf. Okay, remaining thing is only, or remaining temperatures are only T suffix Hf and minus T suffix Cf. So equation will be converted in this particular format. T suffix, two temperatures are remaining, that is the cold fluid temperature and hot fluid temperature, hot fluid temperature and cold fluid temperature. So initial temperature is the hot fluid temperature and the final temperature is the cold fluid temperatures. So these two temperatures are remaining. So difference between these two temperatures will be equal to, now from this particular right side we can take common Q and A. Q divided by A we can take common, because this particular term is present in all three terms. Okay, or these two quantities are present in all these three terms. So we can take common as Q divided by area. Okay, and remaining part we have kept in the bracket as it is. Okay, now we have to convert this equation in the form of a heat transfer rate. We have to convert this equation in the form of a heat transfer rate. So shift this area and this particular bracket on the left side. Okay, on the left side. So this particular, if when you shift this particular area and this particular bracket on the left side, we'll get the equation as Q is equal to area multiplied by T suffix Hf minus T suffix Cf. Okay, whole divided by, in bracket, 1 divided by H suffix Hf plus L divided by K plus 1 divided by H suffix Cf. Okay, now this equation can be written as Q is equal to U multiplied by area multiplied by T suffix Hf minus T suffix Cf, where this U is called as a overall heat transfer coefficient, where this U is called as a overall heat transfer coefficient, and U can be represented as U is equal to, or U can be calculated as U is equal to 1 divided by 1 whole divided by into bracket 1 divided by H suffix Hf plus L divided by K plus 1 divided by H suffix Cf. Whereas this particular H suffix Hf is the convection heat transfer coefficient of hot fluid, K is the thermal conductivity of wall, L is the thickness of wall, and H suffix CF is the convective heat transfer coefficient of a cold fluid. Okay, so if you say that if you are change greatly in any of these three particular values, there will be small change in a overall heat transfer coefficient. Okay, so because it is 1 divided by H suffix HF, so if you it may be noticed from the above equation that if the individual coefficient differ greatly in magnitude, only a change in the least will have any significant on the rate of heat transfer. Okay, इसका मतलब क्या है, जब हम इस तीन कोएफिशिएंट है, एक है दो है कन्वेक्टिव कोएफिशिएंट और एक है थर्मल कंडक्टिविटी. ओके, सो ये तीन कोएफिशिएंट है. सो हम ये सोचे कि हमने एक को बढ़ाया या तीन को बढ़ाया तो ज्यादा कुछ फर्क नहीं पड़ेगा. ओके, सो ओवरऑल हीट ट्रांसफर कोएफिशिएंट में उतना फर्क नहीं पड़ेगा. ओके, जब हमने बहुत डिफरेंस में बढ़ाया तब थोड़ा सा डिफर होगा हीट ट्रांसफर रेट, और हम ये बोल सकते हैं कि ओवरऑल हीट ट्रांसफर कोएफिशिएंट में थोड़ा सा डिफरेंस आएगा. ओके, सो यही हमने यहाँ पे लिखा है. इट मे बी नोटिस्ड फ्रॉम the above equation that if the individual coefficient differ greatly in magnitude, only a change in the least will have any significant on the rate of heat transfer. Getting everyone? Getting everyone? Is there any question, any doubt whether you understood this particular derivation? Simple, we are using Newton's law of cooling and Fourier's law of heat conduction, and we are manipulating the terms, or we can say that we are rearranging the terms and we are finding out one terminology, that is nothing but overall heat transfer coefficient. Is there any question, any doubt? So we'll start the writing part. Okay, so draw this diagram. Draw this diagram. The overall heat transfer coefficient. The overall heat transfer coefficient. I will give you 2 minutes. Please draw it neat and clean. Overall heat transfer coefficient. Okay, also draw the electric analogy circuit. Please provide the appropriate significance for each. Okay, don't miss any symbol or any nomenclature. Okay, so here T suffix HF is the temperature of a hot fluid, and this is the temperature profile we have drawn. Okay, temperature profile we have drawn. So T suffix HF is the hot fluid temperature. T1 is the surface temperature of a wall on hot fluid side, and T2 is the surface temperature of wall on cold fluid side, T2 is the temperature of wall on a cold fluid side, then TCF is the temperature of a cold fluid which is flowing from another side of a wall. H suffix HF is the convective heat transfer coefficient. K is the convective heat transfer coefficient of a hot fluid. K is the thermal conductivity of a metal wall. Then H suffix CF is the convective heat transfer coefficient of a cold fluid. Okay, convective heat transfer coefficient of a cold fluid. Then heat is transforming from hot fluid towards the cold fluid. Heat is transforming from hot fluid towards the cold fluid. So direction of heat transfer we need to show here. Okay. And the thickness of metal wall is L meter. Okay. Or thickness is equal to L. Okay. Then next, draw the electric analogy circuit for this particular diagram. Electric analogy circuit for this particular diagram. So show the appropriate temperature. So first, heat is transforming from hot fluid to the wall surface. Okay, hot fluid to the wall surface. So that mode of heat transfer is a convection mode of heat transfer, and the resistance for this particular heat transfer will be equal to 1 divided by H suffix HF multiplied by area. Okay, then T1 is the wall surface temperature on hot fluid side. Then heat is transferring through the wall, within the wall, and that mode of heat transfer will be conduction, and the resistance for the heat transfer will be equal to L divided by K multiplied by area. So that will be the conduction resistance. Then heat will reach to the another surface on the cold fluid side wall surface, cold fluid side wall surface, and the temperature of this surface is T2. Now the heat will transfer from this surface to the cold fluid. Heat will transfer from this surface to the cold fluid. So that mode of heat transfer mode is convection heat transfer. So that the resistance for this particular heat transfer will be equal to 1 divided by H suffix CF multiplied by area. Okay, and the last temperature is T suffix CF. T suffix CF. Last temperature is T suffix CF. Okay, have you drawn this diagram? Now next, write down, while dealing with the problems of fluid to fluid heat transfer, write down, while dealing with the problems of fluid to fluid heat transfer, while dealing with the problems of fluid to fluid heat transfer, across a metal boundary, while dealing with the problems of a fluid to fluid heat transfer across a metal boundary, it is usual to adopt an overall heat transfer coefficient. It is usual to adopt an overall heat transfer coefficient in bracket capital U. In bracket capital U. Full stop. Which gives the heat transmitted per unit area, per unit time, per degree temperature difference, between the bulk fluids on each side of metal. on each side of metal, on each side of metal. Okay, full stop. Then next, heat flow equations. Heat flow equations. Heat flow equations. Heat flow equations. Okay, so first heat transfer from hot fluid to the wall surface. Hot fluid side, wall surface. Heat transfer between hot fluid. Write down heat transfer between hot fluid and wall surface. Heat transfer between hot fluid and wall surface is a convection heat transfer. 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 Full stop. Then next line, according to Newton's law of cooling, according to the Newton's law of cooling, heat transfer rate will be given as, according to the Newton's law of cooling, heat transfer rate will be given as capital Q is equal to, capital Q is equal to, capital Q is equal to small h suffix hf, small h suffix hf, that is nothing but convective heat transfer coefficient of hot fluid. Convective heat transfer coefficient of hot fluid. Multiply by area, multiply by capital A, multiply by temperature difference between fluid and surface. Temperature difference between fluid and surface. So that in bracket T suffix HF, that is the hot fluid temperature, minus T1. So T1 is the metal surface temperature on hot fluid side. Hot fluid side, metal surface temperature, T1. Okay. Then this will be the equation number 1. Okay. Further, we have converted this equation in the form of a temperature difference. Okay. So write down T suffix HF minus T1, T suffix HF minus T1, T suffix HF minus T1 will be equal to Q divided by H suffix HF, small h suffix HF, that is the hot fluid heat transfer coefficient, convective heat transfer coefficient, multiply by area, multiply by capital A, multiply by capital A. This is our equation number 2. Equation number 2. Then next, heat transfer within the metal wall. Heat transfer within the metal wall. Heat transfer within the metal wall. Heat transfer within the metal wall is conduction heat transfer. Heat transfer within the metal wall is conduction heat transfer. Heat transfer within the metal wall is conduction heat transfer. Then to determine the heat transfer by conduction, we have to apply Fourier's law. So according to Fourier's law, heat transfer within the wall will be given as Q is equal to K multiplied by area, where K is the thermal conductivity of metal wall, A is the perpendicular surface area available for the heat transfer. K multiplied by area multiplied by T1 minus T2. T1 minus T2 are the temperature difference between two surfaces. T1 is the initial temperature and T2 is the final temperature of that particular wall, or T1 is the entry temperature of wall and T2 is the exit temperature of wall. So T1 minus T2 whole divided by L, whole divided by L. So further rearrangement will be in such a manner: T1 minus T2 equal to capital Q multiply by L, capital Q multiply by L, capital Q multiply by L, whole divided by K multiply by A, K multiply by A. Provide this equation as equation number 4. Equation number 4. Then next, heat transfer from metal wall surface Next, heat transfer from metal wall surface. Heat transfer from metal wall surface to cold fluid. Heat transfer from metal wall surface to cold fluid is convection heat transfer. Is convection heat transfer. Okay, my screen is not visible.
No, sir,
Yes,
not
sir.
visible.
Yes, sir.
1 minute, 1 minute. I think I lost connection. Internet problem is there? I think so. One minute. Okay, no problem. We will discuss the write-up part in the next lecture. Okay, remaining write-up part. Okay. So whether you understood or not, this overall heat transfer coefficient, please let me know. Okay, one question from Admane. I have little confusion between conduction and convection heat transfer. Okay. So, Lakshman, you were present for previous lecture when we are discussing about basic modes of heat transfer, conduction, convection, radiation. You were present? You can unmute and you can ask. No problem. You can discuss with me. Dhananjay Admane, roll number 10. You can unmute. So just I want to ask that whether you were present or not. So I will discuss that thing. I will show. Dhananjay, are you there? Okay, so we have written the equation number 4. So convection means what? When the heat is conduction means what? If the two bodies are in a physical contact, okay, or the heat is transferring within the substance, okay, so then that particular heat transfer will be considered as a conduction. Okay, समजतंय का? ज्यावेळेस दोन बॉडी किंवा दोन डिफरंट बॉडी फिजिकली कॉन्टॅक्ट मध्ये असतात त्यावेळेस त्यांच्यात जे हीट ट्रान्सफर होतं एका बॉडीकडून हॉट बॉडीकडून कोल्ड बॉडीला जे हीट ट्रान्सफर होतं त्याला आपण कंडक्शन म्हणू शकतो. किंवा एखाद्या बॉडीमध्ये एका कोपऱ्यापासून दुसऱ्या कोपऱ्याला हीट जाते. ओके, आपण एक उदाहरण दिलं होतं आठवत आहे ना? मेटल रॉड आपण फायरवरती असं होल्ड केल्यानंतर मेटल रॉड एका साईडला हीट होतोय पण आपल्याला थोड्या वेळानं दुसऱ्या साईडला पण हीट जाणवते. ओके, सो काय होतं त्या ठिकाणी तर एका रॉडच्या एका कोपऱ्यापासून दुसऱ्या कोपऱ्याला हीट ट्रान्सफर झालेली आहे. सो ती हीट कुठून ट्रान्सफर झाली तर त्या विदिन द मटेरियल मध्ये ट्रान्सफर झाली. ओके, एका कोपऱ्यापासून दुसऱ्या कोपऱ्याला. तर त्या हीट ट्रान्सफरला सबस्टन्स मध्ये सॉलिड मध्ये जी हीट ट्रान्सफर होते ते एका कोपऱ्यापासून दुसऱ्या कोपऱ्याला त्याला आपण काय म्हणतो कंडक्शन म्हणतो. ओके, आता कंडक्शन फक्त सॉलिड मध्येच होतं असं नाही. कंडक्शन हे गॅसेस मध्ये पण होतं, कंडक्शन लिक्विड मध्ये पण होतं. तर गॅसेसमध्ये कसं होतं, ज्यावेळेस दोन मॉलिक्यूल एकमेकावरती आदळले जातात त्यावेळेस ते फिजिकल कॉन्टॅक्ट मध्ये असतात. तर त्यावेळेस जी हीट ट्रान्सफर, मग त्यावेळेस त्यांचं मोमेंटम पण ट्रान्सफर होतं. आपण गॅसेसची एनर्जी थेअरी आपण बघत होतो, कायनेटिक एनर्जी थेअरी ऑफ गॅसेस. सो ज्यावेळेस ते एकमेकावरती आदळतात त्यावेळेस त्यांची हीट ट्रान्सफर पण होते, एनर्जी ट्रान्सफर पण होते आणि मोमेंटम ट्रान्सफर पण होते. त्यामुळे आपण कंडक्शन फक्त सॉलिडमध्येच असतं असं म्हणू शकत नाही, कंडक्शन गॅसेसमध्ये पण असतं. सो सिमिलरली लिक्विडमध्ये पण कंडक्शन होऊ शकतं, कारण की लिक्विडचे मॉलिक्यूल पण एकमेकावरती कंटिन्युअस आदळत असतात जसं की गॅसेसमध्ये आदळतात. तर लिक्विडमध्ये पण गॅसेसचे मॉलिक्यूल एकमेकापासून जास्त डिस्टन्सवर असतात, लिक्विडचे मॉलिक्यूल जरा जास्त क्लोज असतात. ओके, सो दॅट मोर डॉमिनेटिंग इन लिक्विड. नाव आता कन्व्हेक्शन कशाला म्हणू शकतो आपण? कन्व्हेक्शन जर समजायचं असेल तर तुला परत एकदा जुने लेक्चर बघावं लागते. ओके, तर मी सिंपल भाषेत सांगतो कन्व्हेक्शन म्हणजे काय. समजा जर एक साधं उदाहरण आहे, आपण भूगोलात वगैरे शिकलो होतो की बाबा पाऊस कसा पडतो. ओके, समुद्राच्या पाण्याची वाफ होते आणि ती वाफ हवेपेक्षा हलकी असते आणि ती खूप वरती जाते आणि त्यापासून ढग बनतात आणि त्याला थंड वारा लागला की पाऊस पडतो. ठीक आहे, हे आपण भूगोलात कधी तर 4वी-5वीला शिकलो होतो. म्हणजे काय, ज्यावेळेस एखाद्या गोष्टीचं टेम्परेचर वाढतं, सिंपल भाषेत एखाद्या गोष्टीचं टेम्परेचर वाढतं त्यावेळेस त्या 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 एअरचं किंवा त्या लिक्विडचं किंवा त्या फ्लुइडची डेन्सिटी कमी होते. ओके, हलकी होते म्हणजे काय, त्या फ्लुइडची डेन्सिटी कमी होते आणि त्यामुळे ते ट्रॅव्हल होतं नॅचरली, एका लोकेशन पासून दुसऱ्या लोकेशनला ते ऑटोमॅटिक ट्रॅव्हल होतं. ओके, तर ज्यावेळेस टेम्परेचर वाढतं त्यावेळेस डेन्सिटी काय होते, कमी होते आणि त्यामुळे जर हीट ट्रान्सफर होत असेल, ओके, त्या लिक्विडची मुवमेंट होऊन हीट ट्रान्सफर होत असेल किंवा त्या फ्लुइडची मुवमेंट होऊन हीट ट्रान्सफर होत असेल तर त्याला आपण काय म्हणतो, कन्व्हेक्शन म्हणतो. ओके, आता ह्यात अजून एक दुजोरा देण्यासारखी गोष्ट काय आहे, तर ज्या वेळेस आपण एखाद्या सरफेस पासून फ्लुइडला हीट ट्रान्सफर होते. ओके, एखाद्या सॉलिड सरफेस पासून फ्लुइडला हीट ट्रान्सफर होते त्यावेळेस ऑब्व्हियसली ज्यावेळेस टेम्परेचर वाढतं फ्लुइडचं तर त्यावेळेस त्या फ्लुइडची मुवमेंट पण चालू होणार आहे. राईट आहे, म्हणजे आपण एक साधं उदाहरण घेतलं हीटरचं. जर तुम्ही तुमच्याकडे एक सेपरेट हीटर असेल, तुम्ही हॉस्टेलमध्ये वगैरे चोरून चोरून वापरत असाल तर त्यावेळेस जर तुम्ही लक्ष दिलं असेल, समजा हीटर जर बादलीत टाकला आणि थोड्या वेळ ऑब्झर्व केलं आपण तर आपल्याला काय लक्षात येतं की जे हीटरच्या शेजारचं लिक्विड जे आहे किंवा पाणी जे आहे ते हीट होतंय आणि ते वरच्या डायरेक्शनला फ्लो होत आहे. ओके, आणि त्याची जागा नवीन लिक्विड घेते किंवा नवीन वॉटर घेते, फ्रेश वॉटर आपण म्हणू शकतो. तिथं असणारं दुसरं आजूबाजूचं वॉटर, ती जे गरम झालेलं वॉटर आहे ती वरती आल्यानंतर त्याची जागा दुसरं कोणतरी घेतं. मग थोड्या वेळानं आपण ऑब्झर्व केलं त्या गोष्टीला तर आपल्याला लक्षात येतं की तिचं काहीतरी मुवमेंट चालू आहे, त्या पाण्यामध्ये काहीतरी मुवमेंट चालू आहे. ओके, सो व्हॉट इज हॅपनिंग ऍट दॅट पर्टिक्युलर पॉइंट, की तिथं डेन्सिटी, जी गरम झालेलं पाणी आहे त्याची डेन्सिटी काय होते, कमी होते, त्यामुळे ती वरच्या डायरेक्शनला फ्लो होते आणि त्या पाण्याची, गरम झालेल्या पाण्याची जागा दुसरी कुठलं तरी पाणी घेतं. हा जो करंट फॉर्मेशन होतो, करंट फॉर्मेशन म्हणजे काय, एक फ्लो फॉर्मेशन होतो किंवा एक मेकॅनिझम फॉर्मेशन होतो नॅचरली. तर तो जो मेकॅनिझम आहे त्याला आपण कन्व्हेक्शन म्हणू शकतो. ओके, तो जो मेकॅनिझम आहे हीट ट्रान्सफर होण्याचा, बिकॉज ऑफ अ मुवमेंटम ऑफ अ लिक्विड. ओके, बिकॉज ऑफ अ मुवमेंट ऑफ अ लिक्विड heat is transferring. Okay, so that particular mechanism will be considered as a convection. समजते, मी सोप्या भाषेत खूप सांगितलेलं आहे तुला अजून थोडं जर जास्त कळायचं असेल तर प्रिव्हियस लेक्चर किंवा पहिले जे लेक्चर आपले झालेले आहेत कन्व्हेक्शनच्या बाबतीतले तर ते तू जरा ऐकणं गरजेचं आहे. ओके, किंवा आम्ही ते स्टडी मटेरियल मध्ये पण अपडेट केलेले आहेत, जर तू ते बघितले तर तुला व्यवस्थित समजून जाईल त्या गोष्टी. ओके, आता फोरियरचा लॉ आहे कंडक्शनच्या रिलेटेड, तसाच कन्व्हेक्शनच्या रिलेटेड न्यूटनचा लॉ आहे. सो न्यूटनचा लॉ काय सांगतो की जी ही हीट ट्रान्सफर होते कन्व्हेक्शननं, ती हीट किंवा तो हीट फ्लक्स डायरेक्टली प्रोपोर्शनल असतो कशाला, टेम्परेचर डिफरन्स बिटवीन द सरफेस अँड द फ्लुइड. ओके, सरफेसचं टेम्परेचर आणि फ्लुइडचं टेम्परेचर ह्या दोघातल्या टेम्परेचर डिफरन्सला हीट फ्लक्स किंवा हीट ट्रान्सफर पर युनिट एरिया हा डायरेक्टली प्रोपोर्शनल असतो, असा न्यूटनचा लॉ आहे कन्व्हेक्शनच्या रिलेटेड. ओके, सो तेच लॉ आपण इथं वापरतोय. म्हणून आपण इथं कन्सिडर करताना काय केलं की पहिल्यांदा हे जे कन्व्हेक्शन आहे, फ्लुइड कडून सरफेसकडे हीट ट्रान्सफर होते, तर फ्लुइड कडून सरफेसकडे हीट ट्रान्सफर होते, तर ती कन्व्हेक्शन आपण समजायची. कन्व्हेक्शन मोडनं हीट ट्रान्सफर होते असं समजायचं. ज्यावेळेस मटेरियलमध्ये हीट ट्रान्सफर होते त्यावेळेस कंडक्शननं हीट ट्रान्सफर होते असं समजायचं. आणि ज्यावेळेस मटेरियल मधून किंवा वॉल मधून परत फ्लुइडला हीट ट्रान्सफर होत असेल तर ती कन्व्हेक्शन हीट ट्रान्सफर होते असं समजायचं. समजतंय? आणि अकॉर्डिंगली आपण त्या लॉ प्रमाणे जे रेजिस्टन्स मिळते ते रेजिस्टन्स आपण इथं इलेक्ट्रिकल अॅनालॉगी मध्ये आपण पुटअप केलेलं आहे. ओके, सो अशा प्रकारे आपण ते इक्वेशन लावलेले आहेत. ओके, ज्यावेळेस कन्व्हेक्शन आहे त्यावेळेस न्यूटन्स लॉ ऑफ कुलिंगचं इक्वेशन वापरून आपण टेम्परेचर डिफरन्सच्या फॉर्मॅटमध्ये इक्वेशन फाइंड आउट केलं. ज्यावेळेस कंडक्शन आहे त्यावेळेस आपण फोरियर्स लॉ वापरला आणि टेम्परेचर डिफरन्सच्या फॉर्मॅटमध्ये इक्वेशन फाइंड आउट केलं. परत एकदा कन्व्हेक्शन आहे. ओके, सो from metal surface to from metal wall to cold fluid heat is transferring, so that once again we have to apply the convection law, that is Newton's law of cooling, and that will be equal to Q is equal to H C suffix Cf multiply by area multiply by T2 minus Tf. Okay, that will be the equation number 5. Have you written this? Have you written this? Then once again write down this we have to convert this equation in the form of a temperature difference. Okay, so temperature difference T2 minus Tcf is equal to Q divided by H suffix Cf multiply by area. Okay, so once you done this, once you find out 4 temperatures, we have to put it in the format. We have to add up that equation. Addition should be in a such a manner that left hand side should be added on a left side and right hand side should be added on a right hand side. So we have done this particular thing, and we have determined the U value. Okay, so where we reach, so I think up to this equation number 5 we have reached. So write down this: heat transfer from metal wall surface to cold fluid is convection heat transfer, is convection heat transfer. Therefore Q is equal to H suffix Cf is equal to H suffix Cf multiply by area, H suffix Cf multiply by area into bracket T2 minus T suffix Cf, T2 minus T suffix Cf, bracket complete. We have converted that equation in the form of a temperature difference. So equation will become T2 minus T suffix Cf, T2 minus T suffix Cf is equal to Q divided by H suffix Cf multiply by area, Q divided by H suffix Cf multiply by area. So that will be the equation number 6. Equation number 6. Now adding equation 246, adding equation 246, adding equation 246. Write down adding equation 246. So do addition, temperature addition on one side and right hand side terminology addition on right hand side. Okay, write down equation. Then minus T1 plus T1 cancelled, minus T2 plus T2 will be cancelled, remaining only T suffix HF minus T suffix CF, remaining only T suffix HF minus T suffix CF. is equal to Q divided by A. We have taken Q divided by A common. So Q divided by A into bracket, Q divided by Q divided by A into bracket 1 upon H suffix HF, 1 upon H suffix HF plus L divided by K multiplied by A, L divided by K multiplied by A, L divided by K multiplied by A plus 1 upon H suffix CF multiplied by A. No. Here we have taken A common now. So there will not be A. We have taken Q by A common. So there will not be A inside the bracket. Okay. So my mistake. Do correction accordingly. Okay. So then we have converted this equation in the form of Q. Q is equal to area multiplied by into bracket T suffix HF minus T suffix CF bracket complete whole divided by into bracket 1 upon H suffix HF plus L divided by K plus 1 upon H suffix CF bracket complete. Now this equation can be written as important equation Q is equal to this equation can be written as Q is equal to U multiply by A multiply by T suffix HF minus T suffix CF. U is equal to Q is equal to U multiply by area multiply by into bracket T suffix HF minus T suffix CF. Where U is equal to overall heat transfer coefficient. U is equal to overall heat transfer coefficient. And the equation for U is U is equal to 1 whole divided by into bracket 1 divided by H suffix HF plus 1 L divided by K plus 1 divided by H suffix CF. Getting everyone? So next, it may be noticed, note liha idhar, write down the note. It may be noticed from the above equation that if the individual coefficient differ greatly in magnitude, if the individual coefficient differ greatly in magnitude, Dhananjay, you are misunderstanding. You forgot the concept of thermodynamics now. Okay. So initially I have given the difference between thermodynamics and heat transfer. So open system, closed system, isolated system. You forgot that differences. That don't take that concept in a heat transfer. Okay. So heat transfer is more advanced than the thermodynamics. Okay. And open system means what? If the heat and energy is heat and matter is exchanging, then that will be considered as a open system. When only energy is exchanging, then that will be considered as a closed system. But this concept is very is what we can say that very basic thing. Okay, basic thing. Now you should come out of that particular concept. Okay, and you have to learn the convection and conduction. Okay, system is the very basic thing now. Okay, so you have to come out of that particular concept, open system, closed system, and try to understand the conduction and convection. Don't correlate open system with conduction, convection, and closed system with the convection. If you correlate these things, there will be a fumble about the knowledge. Okay, there will be fumble about the knowledge, because there are n number of examples which are open system but conduction, and there are n number of examples that which are closed system but convection. Okay, so come out of that open system and closed system and try to understand in a broader manner conduction and convection. Okay, so have you notice note, it may be noticed from the above equation that if the individual coefficient differ greatly in magnitude, only a change in the list will have any significance on the rate of heat transfer. Only a change in the list will have any significance on the rate of heat transfer. Is there any question, any doubt now? Okay, we will stop here now. If you have any doubt, any question, you can ask, or else you can put up your roll numbers in the chat box and you can leave.